Right, hi guys, I will solve the rest of the questions of today. So you see, we solved in the class this part A. I will solve now G and J on the whiteboard. Right, so G, the function is given square root of x squared minus 1. Okay. Right, now what's the domain of this function? It's the points except the ones which make the denominator 0, which are plus and minus 1. And also this should be greater than 0, right? So domains are the points in R such that x squared minus 1 is greater than 0, right? So it's basically minus infinity minus 1 union 1 infinity. All right. We also need to find the vertical asymptote and horizontal asymptote. So you see plus and minus 1 makes this function undefined. As they make the denominator 0, so we need to check the limits at those points. So when x is approaching 1 from right, we have the function f of x. Let's write it as in this form, square root of x minus 1, x plus 1. Okay, so you see when we're approaching, when we're approaching 1 from the right, we have some constant in the numerator, and in the denominator we have these products. So as x is greater than 1, we will have something positive, right? But it will be approaching 0, so we will have plus infinity. Okay. And as we did these things, I will not complete them or explain them again and again. So similarly, we have this one. Sorry, it will be this minus 1 from left. It will be minus infinity. We don't need to check minus 1 from right and 1 from left because they are not included in the domain, right? The points between minus 1 and 1, including minus 1 and 1, are not included in the domain. We don't need to check those limits. So we see that x equals to 1 and x equals to minus 1 are vertical asymptotes. Okay. And also for horizontal asymptotes, we need to check the limit when x is approaching infinity. So we have this one. We have this function. So I will rewrite this denominator as in this form in the parentheses of x squared. So we have 1 minus 1 over x squared. Okay. Now what do we have? We can rewrite it as in this form. I can write this x squared outside of the square root, so it will be absolute value of x, and in the square root we have 1 minus 1 over x squared. Okay, so we're approaching infinity plus infinity, so the values of x's are positive, which means this is equal to x itself. And if we simplify them, we will have 1 over the square root of ta, ta, ta. So as x is approaching infinity, what do we have now? 1 over square root of 1 minus 1 over x squared. This will be approaching 0, so we will have 1, right? And similarly, you can compute the limit when x is approaching minus infinity of f of x. You will have the same thing, but instead of x, you will have minus x. So you will have minus 1 over this one. So the limit will be minus 1. Okay. Now what do we have? So let me erase it. So we have x, let's write it here. X equals to 1 and minus 1. Sorry, y equals to. Y equals to 1 and minus 1 are horizontal asymptotes. Okay. So we now find the derivative of the function. First one's derivative is 1 times the second one, which is this, minus the first one times the second one's derivative. So it will be 1 over 2 times x squared minus 1 to the minus 1 over 2 times 2x over this one square, which will give us x squared minus 1. Okay, so what do we have here? X squared minus 1. We have these twos are simplified. This one and this one, they are simplified. Now what do we have? We have x squared. Let's write it with the same color. So x squared over square root of x squared minus 1 over this. Okay, so if you simplify them again or make the basic operations, you will get at the end minus, here let's write it, x squared minus 1 minus x squared over x squared minus 1 times square root of x minus 1, square root of x squared minus 1, sorry. So here you have minus 1, and in the denominator we have the same thing. Okay, and you see this has no solution, so there's no root of this f prime, but it's always less than 0, right? For any value of x, it's always less than 0, so f is decreasing on its domain. Okay, and what else? We need to find f double prime. It will be 3x over this one, x squared minus 1 squared. X squared minus 1. Okay. Now, if it's 0, then x is equal to 0, but it's not in the domain, right? It's not in the domain, so it has no inflection points. Now, remark that plus and minus 1 change the sign of f double prime, so we need to consider them in the table. Now, what do we have? F prime, f double prime, and f. Now we have minus 1. It's not a root of any of them. And we have 1. Okay. Now this on this part, the function is not defined, so we don't care about it. Now, what about this one, this part? So just pick any value. As you see, we already said that it's negative always. But if picking some value from here, you can check if it's negative or positive. So it's negative, and here also it's negative. And what about f double prime? So if x is greater than 1, you will have something positive here. It's always positive, and this is always positive. So you will have something positive there. And if it's less than minus 1, in the numerator we have something negative, so it will be negative. Okay, so the function f is always decreasing, and here it's downward. Here on this interval, it's upwards. Now what do? We sketch the graph using this table. Okay. Let's note first the asymptotes. So we have x equals to minus 1 and x equals to 1. And also y equals to 1 and y equals to minus 1 are horizontal asymptotes, so we need to note them too. So this is 1, and this is minus 1, right? Now you see the function is decreasing and upward, so it should look like this, right? So when x is greater than 1, it should look like this. It's decreasing and upward. Now you see when we're approaching 1 from right hand side, we computed here, it's approaching infinity, right? So let's note that this is hard. Right, this is horizontal asymptote. So when we're approaching 1 from right hand side, it's approaching plus infinity, right? So it should look like this, right, for that part, right? And when we're approaching plus infinity, as in here, as x is approaching plus infinity, the function is approaching 1. So as this y equals to 1 is horizontal asymptote, so it should look like this. And similarly, for that part, you see it's decreasing and downward, so it should look like this, right? So, and also we can use these limits too. When we're approaching -1 from left, -1 from left here, it's approaching minus infinity, so it should look like this, okay? And what about this part? When we're approaching minus infinity, when x is approaching minus infinity, the function is approaching -1, so we will have this one, okay? And on this interval, on -1, comma 1, it's not defined. There will be no graph on there, right? So this is the graph of the desired function. Now we have the part J. Okay, 5J. We are given this function f of x sinus x over 1 plus cosinus x. Now the domain of this function again, domain of f is the set of points x's, so that 1 plus cosinus x is not equal to 0. All right. Now, what are those points? Cosinus is 0 if it's sorry, let's rewrite it. Cosinus x cannot be equal to -1. All right, it cannot be -1. So cosinus is -1, gets the value -1 if x is a multiple of pi, an odd multiple of pi. So what do we have? We have r except these points. K is an integer. Okay, we subtract the points and which are odd multiples of pi, right? Cosinus is -1 here. It's -1 on what? On pi. And what else? If we add 2 pi, it will be -1 again on 3 pi. And adding 2 pi will give 5 pi. So the odd multiples of pi give us cosinus x -1. So we need to get rid of these points. All right. So we have this set, this domain. What else? We note that f of 0 is sinus 0 is 0. So f of 0 is 0. And f of x is equal to 0 if sinus x over 1 plus cosinus x is equal to 0. Then what do we have? Sinus x should be 0, which gives x should be, when sinus is 0, when is sinus 0, it's on 0 or pi, right? So we can say k pi, okay, for any k in integers. Okay. Now, is, for example, pi in the domain? No, right? The odd multiples are not included in the domain. So we can only write here 2k pi, because only the even multiples of pi are included in the domain. So we can take these ones only. Okay. As pi is not in here, right? Pi is not in the domain. We cannot solve this equality by saying x equals to pi, right? Only we need to take the ones in the domain which make this function 0, which are the even multiples of pi. All right, now what else? We need to find f prime and equalize it to 0. So the first one's derivative is cosinus x times the second one minus the first one times the second one's derivative, which is minus sinus x. So we get plus sine squared x there, right, over this one's square, cosinus x squared, which is cosinus x plus 1 over 1 plus cosinus x squared. How did we get it? Just distribute this function, cosinus x plus cosinus squared plus sinus squared. Cosinus squared plus sinus squared is equal to 1, so we have this. Now we can simplify them and get 1 over 1 plus cosinus x. And this is 0. This is not equal to 0 for any value of x. But remark that 1 plus cosinus x is 0 when x's are in here. Okay, we need to observe them on the table also. We need to consider them on the table. Okay. And also we need to find f double prime, which is here minus, so we can rewrite this as in this form. This is equal to 1 plus cosinus x to the minus 1. So we take this one's derivative. We have minus 1 times 1 plus cosinus x minus 2 times this function's derivative, which is minus sinus x. So what do we have? We have sinus x over 1 plus cosinus x squared. And this is 0 only if x's are 2k pi, right? Where k is in the integers. So these are inflection points of the function. Now let's make the table. So we have f prime and f double prime. And f. Okay, so let's note the points 2 pi, pi, 0, pi. Here 2 pi. It goes on, right? So is 2 pi a root of f prime? No, it's not. There's no root of f prime, right? So we can write them as in this form. Okay, and f double prime has roots when we have the even multiples of pi. So this is a root of f double prime, and this is also, and this is, all right? Now, what's the sign of f prime? First, we need to find that. So you see, we have 1 over 1 plus cosinus x. We know cosinus x is in between 1 and minus 1. So if we add 1 there, we will have 0 cosinus x and 2. So 1 plus cosinus x is in between 0 and 2. So it means it's positive. As we have already something positive in the numerator, so this is always positive for any value of x. So let's first note that this is always positive, no matter what the value of x. What about f double prime? We can only pick some value and compute the observe the sign of f double prime. For example, we can pick any value from here between 0 and pi. Between 0, this is always positive, right? 1 plus cosine squared is always positive. Sinus x is positive between 0 and pi, so it will be positive. So the only sinus x changed the sign of f double prime. Between pi and 2 pi, sinus x is negative, so we have negative there, right? And between 0 and pi, the value of sinus x is again negative, so we have 0. It means we have this angle now, right? From 0 to pi, so we're below the x-axis. That's why it's negative. Similarly, you will have plus theta. Okay. Now, what do we have here? F prime is always positive, so the function f is always increasing, right? On its interval, it's always increasing. And what about these parts? It's upward, downward, upward, downward. It will go like this, okay? Downward, and then upward. But it's always increasing. Okay, so let's sketch the graph of this function now. All right. We forgot to compute the vertical asymptote and horizontal asymptotes, right? So what are the vertical asymptotes? Let's compute that too. Here I'm computing that limit of. So the points which are odd multiples of pi makes this denominator 0. That's why we need to compute the limit on those points. Let's compute only pi. The other ones will be the same. So when we're approaching pi from left, we have this function sinus x over 1 plus cosinus x, right? So you see when x is equal to pi, here in the numerator, we will have 0. And in the denominator, we have again 0. So we have 0 over 0. We can apply L'Hopital rule. So in the numerator, we have cosinus x, if we take the derivative of that. And in the denominator, we have minus sinus x. So we have minus cotangent there. And it will be, recall the graph of cotangent, it will be infinity. From right, we need to compute that too. So we will have the same function f of x inside of the limit. Now it will be again sinus pi is 0 and 1 plus cosinus pi is 0. So we will have again 0 over 0. We take the derivatives by applying L'Hopital rule. We will have the same function cosinus x over minus sinus x. Again, when we're approaching pi from from the right, we will have minus cotangent, so it's minus infinity. Okay. Now we can, right? We can sketch the graph now. So let's note pi, minus pi, minus 2 pi, and go on. Here we have 2 pi, 3 pi, okay? Now, recall that the function is equal to 0 if x is an even multiple of pi. So these are the roots of the function, okay? Now let's write them here. These are the vertical asymptotes of the function because they make the denominator 0, these points, and we computed only for pi, but they will be the same for any odd integer, and they make the limit of the function infinity, minus and plus infinity, so they will be vertical asymptotes. Now, what else? Here we see that the function is always increasing, so it will be look like, for example, let's find it only here between pi and minus pi and pi. This is minus, sorry, minus pi and pi. So it's increasing, right? It will be like this, and here it's also increasing but upward, so it will look like this. Now we know this point also is on the domain, right? Sorry, on the graph, 0, 0. So it's increasing and upward after 0 till pi. So it will be like this. You know, when we are approaching pi from left, it will be plus infinity. So we have this. And from left, sorry, when we are approaching, sorry, I didn't compute that, but minus pi plus, so minus 5 plus will be the same with that. So it's like this. So as you see, it's downward and increasing. So always the graph of the function look like as in here. Okay. It will be go like that. Okay, it's continue from here, for example. And what's that point? It's minus 4 pi, as we said. On even multiples, it's 0, right? And here also, it will be the same for 4 pi. Okay, so this is the graph of the function. All right, I hope it's clear. Now the question 6. So we will find the limit of the given functions using L'Hopital rule. Okay, so we did already that f. We only do the rest of the question. So here we have x squared minus 1 over x squared minus x. We see when if we put x equals to 1, we will have 0 over 0, so we can apply the rule. So how do we apply it? So we take first the derivative of this one, which is 2x, and the derivative of this function is 2x minus 1. Now if we put x equals to 1, here in the numerator we will have 2, and in the denominator we will have 1, so the limit is 2. What about this? When we put x equals to 0, sinus 0 is 0, and tangent 0 is again 0. The definition of tangent is sinus over cosinus, so we will have 0 over 1, so we get 0, right? Now we have 0 over 0. We apply the rule, taking the derivative of the first one gives 4 cosinus 4x, and we take the derivative of the denominator. We already did in the first classes, I guess, or the second one. So we know how to, we know the derivative of tangent, second squared. So we have this one. All right, now if we put x equals to 0, in the numerator, we will have cosine 0. It is 1. So we have 4 there. 4 times 1 gives 4. Second squared 5x. The definition of second is 1 over cosine. So here we have 1 over cosine squared 5x. So we have 1 there again. We get then 4 over 5. And in here, now if you plug x equals to 0, you will have 1 minus 1, which gives 0. And in the denominator, sine 0 is 0. So we will have 0 over 0, right? Then we can apply the rule, L'Hopital rule. So taking the derivative of the first one gives 2e to the 2x, and the derivative of the second one is cosinus x. So if you plug x equals to 0, here in the numerator we have 2, and in the denominator we have 1, so we get 2. We did this in the class, so let's look at J. Now, when x is approaching infinity, we have e to the x over 10, so it will be approaching infinity again. And denominator is approaching infinity too. So we have infinity over infinity, then we can apply the rule, L'Hopital rule. Now, taking the derivative of the first one, we'll give 1 over 10 times e to the x over 10. And the second one's derivative is 3x squared. So we have this now. As you see, we have still infinity over infinity. That means we can apply the rule again. So we take the derivative of this function now. It will give 1 over 100 e to the x over 10 over this one's derivative, which is 6x. Now, if x is approaching infinity, we have again infinity over infinity. We can apply the rule again, and it will give us this now. Now we got rid of that x, right, in the denominator. So we have this function now. Now x is approaching infinity, so this will be approaching infinity. Infinity over some constant will give us infinity again. All right. So this question was easy. Let's find that D. This is the last question. We already did C, the part C in the class. So we have 7, D, sorry. All right, the function is f of x, which is equal to x squared minus 3 e to the minus x. Now, what's the domain of this function? It's real numbers, right? There is no point which makes this function undefined, right? This is x squared minus 3 over e to the x. E to the x is never 0, so the domain is all real numbers. And also note that f of 0 is equal to minus 3, and f of x, if f of x is equal to 0, then x squared minus 3 over e to the x is equal to 0. It gives x is equal to plus minus square root of 3. All right. Now, as there's no point which makes this function undefined, we don't have to look at the vertical asymptotes, only the horizontal asymptotes. So what are the horizontal asymptotes? We need to check the limit when x is approaching infinity. So we have x cubed minus 3 over e to the x. So we have infinity over infinity, right? When x is approaching infinity, we can apply the rule, L'Hopital rule. So the limit of the first one, the numerator, is 3x squared over e to the x, and the second one's derivative is the same. And we can apply the rule again because we have infinity over infinity. So we have 6x over e to the x. As you see, we need to apply the rule again. I'm sorry, it's x squared. I made a mistake there. So here we have, what do we have here? It's 2x over e to the x. Now we apply the rule again, 2 over e to the x. So x is approaching infinity, e to the x is approaching infinity. So we have 2 over infinity, which gives 0, right? And also limit of this function x squared minus 3 over e to the x. We have again infinity over infinity, so we apply the rule and get here I limit x is approaching minus infinity, 2x over e to the x, right? So we apply the rule again, infinity over infinity. So we have 2 over e to the x. All right, now e to the x, when x is approaching minus infinity, e to the x is approaching 0. So we have 2 over 0, which gives plus infinity. All right, so the only asymptote, the only horizontal asymptote is y equals to 0. Okay, which means the x-axis. Right, now let's compute f prime. Here we have f. So we have product, we apply that rule, 2x times e to the minus x plus x squared minus 3. And this one's derivative is minus e to the x. So minus e to the minus x. Now if we write it in the parentheses of this, we will get x squared minus 3 minus 2x, okay? And we can rewrite this one as in this form, x minus 3 times x plus 1, which is equal to 0. So it gives x equals to 3 and x equals to minus 1 are the critical points. As you see, they are in the domain, so they are the critical points of the function f. Now f2 prime, we take the derivative of this one. Okay, so we have product again. Now the first one derivative is e to the minus x times the second one minus plus the first one is minus e to the minus x, that's why we get minus there, times the second one's derivative is 2x minus 2. Okay, this one's derivative is here. Now if we write it in the parentheses of e to the minus x, what do we get? The first one is here. The first one gives x squared minus 3 minus 2x, and the second one gives minus 2x plus 2, so we get this one. And if we equalize it to 0, what do we get? So this one should be equal to 0. And what are the roots of this function? If you have a quadratic polynomial, then the roots of this polynomial are these ones, minus b plus square root of delta over 2a, and the other root is this. So what's the delta here? And delta is b squared minus 4ac, okay? And it's by that computation, we find delta 20. So the roots are 4 minus b gives 4 plus minus square root of delta over 2a, which is 2. Okay, so we have 2 plus minus square root of 20 is 2 square root of 5. So 2's are simplified, so we get square root of 5. So these are These two are the roots of this polynomial, which means they are, as they are in the domain, they are the inflection points. Okay. Now let's find the table. So what do we have here? You see, we have -1, this, and these 2 points. Okay. Now we have -1, 2 minus square root of 5, 3, and 2 plus square root of 5. Okay, f prime, f double prime, and f. Now this -1 is a root of f prime, so we write it like this, and the rest is this. And this is only the root of f double prime, and this too. And here we have. All right, so what's the value of f prime when x is greater than 3? Just pick any point here and try if you get something positive or negative. You will see it will be negative. Okay, and then you will get plus, plus, and negative. I don't do the same explanations. It's always the same method. So just pick any point and try to and observe what sign you get there. Okay, so plus, plus, negative, negative, and plus. Okay, you have this function. You just pick any point from here and try it here if you get plus or negative. So you get plus, and then you need to change the sign, right? That's actually you need to find you need to pick a point from here and try it again, because you don't have only a polynomial but e to the -x there, right? Though it's always positive, you need to only check this one. So it gives, this is decreasing, increasing, and increasing, decreasing, decreasing, upward, downward, downward, upward, and upward. Okay, so what do you have? Let me erase this part. We have this one. So we have minus square root of 3. This is a root, right? Here we have. These are the roots of the polynomial. And we have -1, 2 minus square root of 5. We have square root of 3, which is another root of the function. And this 2 plus square root of 5. Right, now you see it's upward and decreasing, so it should look like this, right? And you see the limit of the function when x is approaching plus infinity. You see it's approaching 0, so it will be like this, right? It's approaching 0 when x is approaching plus infinity. And it's decreasing and upward, so it cannot be something like this, right? It will be increasing. That's why it's something like that. So you will have this. Okay, here it changed. These are the inflection points, right? Remember this and this. These are the inflection points. So it will change its concavity there. Then it means it should be like this. Downward, right? But it needs to cut the graph, the x-axis at there, so it will be something like this. Okay, there it cuts the graph of the function. Right now, what do we know? We also know f of 0 is equal to -3. So it should cut the graph, the coordinates on that point. Okay, so it should be like this, right? Now it needs to change its concavity at that point. So we have here something like that. Okay. Now, as you see, so between between 2 minus square root of 5 and 3, it's like this, increasing and downward. So you see, it's like that. Now, what else do we know? It should cut the coordinate system here at that point. And you see between -1 and this point, it's increasing and upward. So it will look like this, right? Now, then we need to continue like that. So here we have something like this, right? It's increasing and upward. Okay, then what else? It's decreasing and upward, so it should look like that. Thus, it will be like this, right? So it's decreasing and upward, so it's like that. Okay. All right, only this one was the asymptote, right? Y equals to 0. So as you see, for plus infinity, right? Not that part. If that was also equal to 0, then we would have something like this. Okay, then the graph cannot cut the x-axis if that was also equal to 0. But here we have only that one. When x is approaching plus infinity, we get 0. We have only there as the horizontal asymptote. Okay, so this is the graph of the function. All right, so if you have any question from these ones, you can write me email or you can visit me on Friday in Dolapdere campus. Okay. Right. So see you and good luck with the exam.